Okay, welcome back to part 2 of the supply chain lab and the use of averages. If you recall, in the last video, we showed how to use a Monte Carlo simulation to answer a question that came from the executive team about whether or not we could support a promotion that was going to increase demand by 50%. And what I want to do in this video is talk about where the data came from and how to create this type of analysis from the data. So let's come here. This is some history that we've got over the course of a few years. So if you see, this data starts back in January of 2019. It comes all the way, there's 153 different instances that we've got where we've ordered these products and we've received them. And it ends in January of 2025. Today's date is February 27th of 2025, so only about 7 weeks ago. But I've got 153 different instances of this where I can use this data in order to create my analysis. Up at the top, you can see the averages. It's 70 days or exactly 10 weeks. We knew this. We said it was 10 weeks, and it's 1.887 is the standard deviation. We said it was 1.89. That's the 3 digits. So this is where the data comes from. So let's see what we can do with this data. So the first thing we want to do is create a histogram, right? So the longest lead time in here, this is telling me the maximum number in this column here, which is the lead times from the actual data, was 15.14 weeks. The minimum was 5.71 weeks. Here's my table for my histogram data. My lowest number, I'd like to have that be less than my lowest, which it is. My lowest was 5.71. I've got a 5 here. My largest number in the histogram table should be higher than my highest, which it is. What I'm going to do here is I'm going to come in here and I'll look in this column and I'm going to say how many times count if the number in here is less than or equal to 5. We know that that's a 0 because 5.71 was the lowest. In the next number, we're going to go through and we say, okay, how many times was it greater than 5, but less than or equal to 6? And that's a 1. One time it came in between 5 and 6. How many times here was it greater than 6, but less than or equal to 7? Well, that was 7 times, etc., etc. We fill out this table. You can see at the bottom, if I sum up the total number of all these frequencies, it's 153, which it should be. That's how many data points we had in our table. So what we want to do now is let's take a look at what this looks like on a graph. So we've got 2 things on the graph here, right? The bars, the blue bars, is the actual data from our table over here. You can see 5, there's no bar because that was a 0. 6, you can see where that shows a 1 because that's a 1 there. 7 is 7. 8 is 16. So that's just following this. But what I want to do is see, how does this data that I actually pulled in my histogram, how does that compare to a normal distribution? We made the assumption when we did the Monte Carlo simulation in the table that it was a normal distribution, and I want to check and see how accurate my assumption was. So I'm going to go in here, I'm going to use the norm.dist function to come in here and pull different numbers for each one of these numbers. And then I'm going to create, using the orange bar here, not a bar, but the orange line rather, shows what the normal distribution looks like overlaid on top of my actual data. And as you can see, this looks pretty good, right? This orange bar looks to me like it fairly well follows a normal distribution. So I feel comfortable in the assumption that I used that this was going to be a normal distribution. Okay, now some of you may be looking at this saying, hey, that doesn't really look too much like a normal distribution. Look at number 9. My actual data was way above the normal distribution. And look at number 10. It was way below a normal distribution. Everything else is looking pretty good, but these 2 numbers here look like they're actually flipped. I don't really like that very much. So what does that really mean? Okay, if you think that this doesn't look like a normal distribution, let's take a look and see how we can create our own custom distribution to exactly match our data. So we're going to come here to the custom probability distribution tab, and let's see how we can do that. At the top, we've got the data that we've already shown previously. Here's all of the data, the 150 different points that we had, and here's the percentages of that. That's all this is saying, is that for a for a 6, I had one occurrence out of 153. That's 0.65%. For a 7, I had 7 instances out of 153. That's 4.58%. For an 8, I had 16 out of 153. That's 10.46. And then in this column, F is just the running total, right? For 0 through 6, it's 0.65. If I want to figure out what the 7th is, I just add these two numbers together. So the total cumulative percentage for 0 through 7 cumulatively is 5.23. Likewise, for 0 through 8, it's 15.69. So now I want to come through here, and I would like to have more than 153. So I'm going to build another table with 10,000 trials like we did before. 10,000 is a good number to use. And I'm going to go into my table here. I'm going to use my XLOOKUP function here to look into my table here. I'm going to go in here again with a random number. This is something between 0 and 1. And I'm going to look where this 0, the number that comes out of there, falls between this 0.65 and 100, which would be represented as a 1. And I'm going to go in there and come back out with what lead time does that correspond to. So in this particular case, I went in with a random number and it came out with a 10. In the second one, I went in with a random number and I came out with a 13. In the third one, I came out with a 9, etc., etc., etc. So what I want to do now is I'm going to create another histogram, and this time I'm going to go in here, I'm going to say, okay, 6. How many times in this whole column of 10,000 did I come up with a 6? And that's 57. How many times did I come up with a 7? 478 times. And out of 10,000, that's 4.78%. So now what I want to do is come over here and let's take a look at a graph of the two of these on the same series. So the blue rectangles are what the original data was. 0.65% for 6. It was 4.58% for 7, etc., etc. And the orange bars are going to be what just came up from my 10,000, right? So 6 here was 0.57%, which it shows right up here. I've got 7 shows me 4.78%, which it shows right up here. And as you can see from this, this tracks very, very, very well. So, 2 things to take away from this. If you thought that this chart right here indicated that we had a standard normal distribution, then you're easily use that for your development of your Monte Carlo simulation. But if you looked at this and said, hey, you know what, there's 2 of these bars here that don't really track well for me, I'm not real comfortable with that, here's a way that you can go in, create your own custom distribution, which is right here. So instead of a standard normal distribution, I would go use the exact same procedure here, but instead of this norm.inv, I would come in here and I would use my custom probability distribution right here for each one of those 100,000 trials, and I would use that, and then we would likewise use the same function you did here for finding the maximum. But what this allows you to do is if you didn't feel comfortable with this being normal, no problem. You create your own custom distribution, but it feeds into the same Monte Carlo simulation, and you work this out and you use whatever this comes out to be to be able to tell your team, hey, this is how many weeks it's going to take me in order to be able to feel comfortable that we can support that uptick in demand. So I hope this was helpful. I hope this helped you understand how you can use either a normal distribution, make that assumption if the data shows it, but if it doesn't, go into your actual data and use your own custom probability distribution to do the same exact analysis and come up with the same type of an answer. The answer might be slightly different using your custom probability distribution, but it's going to lead you to the same place where you can use this data in order to come back and give a good answer that's supported by the data. So thanks for your attention. I hope this helps, and please join me for more videos like this on how you can use data and analytics to support your decision-making process in supply chain. Thank you.